of the work we've been doing is looking at the inside-out growth and outside-in quenching of galaxies, particularly galaxy disks, so around 5% of cosmic time. This is using maps of H alpha emission to trace star formation at redshift 0 using the Haggis survey. This is H alpha galaxy groups imaging survey. This is a narrowband imaging survey, and then redshifts 0.7 to 2.6 using Camelus 3D. This is a 75 byte BLT program tracing star formation in galaxies, also the kinematics using the very powerful KMOS instrument on the BLT in Chile, which allows you to observe 24 objects at a time in the near infrared with little mini Haggis. Haggis, it's a group survey. Group definition in this case is from Sloan, so we get calibrations of halo mass. And we choose objects between 10 to the 12, so sort of Milky Way, halo-like, to, well, cluster-like, 10 to the 14 at the maximum end. So we're looking at the environmental effects, how that influences the distribution of star formation in galaxies. And this is what we get. So this is a continuum emission map, and this is a, when you subtract continuum emission star formation and H alpha emission, you see the nice spiral lines in this case, and also evacuated bar region, which is kind of typical in some of these objects. This gives you a major axis radial profile, which looks like this. And what happens because of the evacuated bar is it pushes the half-light radius of H alpha out a little bit further than the continuum. So you can end up with what looks like rows just above being evacuated. So this shows H alpha emission. So this shows galaxies with H alpha emission. So the passive galaxies have been excluded from this plot, they're more compact. We're looking at the continuum of half-light radius versus stellar mass, and we see a nice relation. Not so exciting, so I'll move to the next one. Now we're looking at the half-light radius of H alpha versus stellar mass, and the line through those points here, this is just the line from the previous plot, it's not a fit or anything like that. So it shows you that the H alpha scale is in many cases similar to the stellar scale, although there is this cloud of objects with smaller H alpha sizes. And if we look at the ratio of those two numbers, which is the sort of metric I'm using in this talk, you see this sort of ridge where the H alpha sizes are consistent with the stellar sizes, and then this cloud of objects with smaller H alpha sizes. In practice, well, let's go back. In practice, now I finally introduce the points. The blue points are the central galaxies in these groups. The rest of these things are satellites divided into two bins of halo mass at 10 to the 13. You see that most of these objects down here are satellite galaxies. The centers tend to be pretty similar, have similar extents in H alpha as they do in their stars. So this suggests that this is an environmental effect, quenching the star formation from the outside in. So again, this sort of outside in quenching in the lower edge of the universe. This is a little bit clearer. Well, let's just look at this. So this is work from my student Pizzati. We did a similar work. He focused on the Coma supercluster, and they had H1 data. So they looked at this metric as a function of the deficiency in H1. Where you have an H1 normal galaxy, they have a ratio of 13:1, so consistent with these objects. Star formation traces the stars. And for the deficient H1 objects, the H alpha is also more compact. So all very consistent with an with a stripping scenario where the gas is more easily removed from the outer parts of galaxies. And with the Haggis data, we can now look at this size ratio as a function of the offset from the main sequence. This is the star formation rate, global star formation rate of the galaxies normalized by the main sequence value. So what the typical star formation rate should be of a galaxy of their stellar mass. And you see clearly this correlation tells you that the galaxies below the main sequence are also more compact in their H alpha emission. So the star formation is more easily suppressed in the outside of the galaxy. And most of these galaxies down here, as I said before, these are satellite galaxies. So because of the nature of this sample, we're looking at groups and we see this kind of environmental suppression of star formation in the outskirts of satellite galaxies. We don't have the sensitivity, we don't have the sample to do this for central galaxies. So move on, these are typical examples. One more thing from Haggis. we look at the continuum profile and classify this. So if you've got a certain index greater than one object, so more like an elliptical galaxy, classify it as such. But if you have an exponential disk, then there's three types of exponential disk: pure exponential type 1, a truncated exponential type 2, or an anti-truncated exponential type 3. And if you divide the galaxies into passive and star forming, and then look at the fraction of these different types for each of passive and star forming, you see that the star forming population, there's a lot of these type 2 galaxies, these truncated exponential stellar disks, which don't really exist in the passive population. These are sort of plate-type spirals of regular galaxies, so this is interesting. Something happens to those, and that is made up for either with the sort of elliptical type galaxies or type 3s, so where you have the shallow outer disk. And somehow this seems to be something happens which drives the generation of these type 3 profiles when you become passive. If you look at the distribution of this H-alpha continuum size ratio for each of these types, you also find that the type 3s typically have smaller H-alpha continuum size ratio. So it seems to be somehow cotemporal. But this suggests that gravitational interactions have to be important in order to rearrange the stellar orbits that only remove gas. Now, going to higher redshift KMOS 3D, a big program, collaboration that we have going in Munich. The idea is we follow 3D HSC galaxies with KMOS. 3D HSC gives us near infrared selection if we have fair selection across the main sequence, down to low star formation rates because we go very deep, etc., not much time. Then a lot of work goes into doing the background subtraction, so we're able to get that to low surface brightness, derive H-alpha images and major axis profiles. We fit the images in 2D. The H-alpha we fit with an exponential, so this is convolved with PSF. And the stellar continuum, we do this both using the KMOS continuum and the HST data convolved or not to the KMOS PSF, just to be consistent and careful, but everything gives us consistent answers. So we get the same plots. Continuum size, stellar mass. These are also keyed by environment, let's see what's there. Consistent with the Haggis result is that move down, so more compact in the stars. The Haggis line is the black line, not surprising. H-alpha, they're also more compact in the star-forming disks, high redshift, and they're at low redshift, but not by so much. So that if you look at the ratio of the two, the H-alpha disks are typically slightly larger than the stellar disks, but within a reasonably small range here. And the fact that they're larger tells you that we're really witnessing inside our growth of galaxies at this redshift. So these are very gas-rich galaxies, redshift 1 to 2, dense molecular gas, which has more momentum than the old stars, and this tells you as well that the gas is dense and it's more difficult to strip, which seems to be the reason why we no longer. How did I get error? Oh, yes. Well, we no longer get these low star formation rate compact H-alpha galaxies that we saw in the low redshift universe. Maybe these things, at high redshift, these things are still more extended in their star forming disks, and you just change the normalization of the star formation rate in those galaxies. So something else is going on. Stripping is probably more difficult, and we can embrace the scatter. So now I'm no longer keying by environment, I'm keying by disk type. The blue points are all not only well fit by an exponential, but they're also in their H-alpha, but also kinematically they have every signature with respect to a normal relaxed disk at high redshift. The black things are kinematically complex. The red things have a continuum surface profile with an n greater than 2. So if you remove those things, you get a tiny scatter with a sigma of 0.17 x, which is nonetheless still significantly more than our measurement errors. These are errors derived from bootstrap versions of our data cubes, which are then processed in exactly the same way, etc., etc. So I think embrace the scatter. We're already seeing that we've reduced the scatter in this relation by removing these kinematically disturbed galaxies. And this is consistent with stacks from 3D HST. This was work done by Eric Nelson 3DHST is beautiful data, very high spatial resolution, but they don't have the same depth that we do. So they do this in stacks, low to high mass, 3 bits of star formation, and again, you see this median profile of H alpha, which going from below the main sequence to above the main sequence is just a change in normalization. So again, very different from the low redshift universe. So to conclude, high redshift disks row inside out by a star formation, and for regular N of 1 rotating disks, the scatter is quite small, but not as small as the measurement error, so we're looking to probe deeper into that. At redshift 0, they mostly stop growing in size, at least through star formation. And at redshift 0, the outer disks to be preferentially quenched, probably due to satellite-specific processes. And at the moment, with this bit of Haggard sample, I just don't have the data to look at other types of processes because our quenching galaxies are satellites. But maybe with Saturn and Magna, etc., we should be able to look at this in central galaxies. And these things to involve gravitational interactions as well as pure round pressure stripping in order to generate these compact cores and shallow outer disks that you get with these type 3 type profiles in stars. And of course, there's a lot more work to be done. Thank you.
Thanks, Dave. I have a few questions. Yes. All right, so the gravitational interactions, is that like harassment or minor workers?
So simulations of this kind of, well, okay, it's like the understanding of the origin of type 3 type profiles, so these shallow outer stellar disks, is not great. With very nearby galaxies, there seems to be 2 types. One of which describes where the outer disk profile, so the outer exponential, the shallow exponential, is actually described in a halo. So it would theoretically have a different position angle or density than the main point, but you fix that when you derive these profiles. And the other type where that doesn't appear to be the case, so this is really in the disk. And simulations are also lacking. So I think there is suggestion that tidal harassment, tidal interactions or minor mergers can do this. Yeah, we need more work.
Is it moving mass from outside?
Is it moving mass from outside in? Because I thought of these as stripping the outer disk, and then so only star formation is in the center, like Kinney and Koopman.
So that's true in terms of the star formation, right? But the stars, they seem to be moving both in and out in order to generate these type 3 profiles.
Yes, done.
So how do you define your environments at high redshift and low redshift, and how do they differ?
Yes, so at low redshift, this is purely a group catalog. This is the Agnes group catalog from Sloan. At high redshift, we have a sophisticated method using the underlying 3DHST sample. This is the bulk of Matteo Pizzati's PhD thesis. He's writing a paper now, which should be finished fairly soon. We've got pretty good, robust derivations of environments at high redshift now because you have fairly complete redshifts with the GRISM accuracy, which is good enough to do this quite well. And we calibrate this using mock catalogs in order to get, well, actually for each galaxy we get kind of a probability that it's essential or a satellite, and also a full PDF of the halo mass by matching to the mock catalog. So this will be we're going to make this catalog public soon, so people can use it in the deep fields. And it's looking quite exciting also for other purposes, but we're going to use it for cameras, of course.
The next speaker sitting up. Last question.
So yeah, have you? So H alpha, it's really dust. Well, it's affected by dust. So have you thought about using it for micron or something else to just take into account the dust?
It would be wonderful. Of course, the problem is I don't have the data. I think, yeah, this is always one of the big uncertainties for this kind of measurement, right? So you limit yourself to one emission line or one measurement of anything. And in practice, you know there's going to be an influence for dust in this case. So it could mean that galaxies, I would expect that if anything it means that galaxies are more compact in their star formation than in the H alpha, but yeah, it would be good to have, data, but of course, realistically, maybe at least it would be good to have some kind of recipe to try and understand what it would be on average. Don't have that at the moment.
Okay, thank you. Anyone with that